In this segment, we're going to cover related rates, and this is another application of taking the derivative of an expression and then solving for the rate of change, the derivative that we're looking for. So once again, if you've got g composed with f of x, take the derivative of g with respect to f, and then take the derivative of f with respect to g, with respect to x. Okay, so basic idea, differentiate the expression with respect to the independent variable using the chain rule where applicable, then solve for the desired rate using the given rates. Okay, so here's an example. The volume of a sphere of radius r is given by the expression 4/3 pi r cubed. Now, supposing that the radius of the sphere is increasing at a rate of 1 centimeter per second, at what rate is the volume of the sphere changing? When the radius is 10 centimeters. So notice what you've been given. You've been given that dr by dt is 1 centimeter per second, and you're told that you want to know what dv by dt is when r is equal to 10. Okay, so taking the derivative with respect to t, dv by dt is the right-hand side, take the derivative with respect to r, and then multiplied by dr by dt. So the derivative of 4/3 pi r cubed is 4/3 pi times 3r squared, and then r was a function of t, so you have to multiply by the inner derivative, dr by dt. Okay, then dv by dt is 4/3 pi times 3. You were told that you wanted to know what the rate was when r is equal to 10. So here put in 10 squared for r squared times, and you're told that dr by dt is a constant rate of change, 1, so times 1. So you get 400 pi centimeters cubed per second. Okay. Let's try something slightly different. You have v of r equals 4/3 pi r cubed. Now you're told what v is, and you have to work out what dr by dt is when r is equal to 10. And so in this case, you're going to differentiate, use the chain rule, and you're going to have to solve for the expression. You're going to have to solve for the derivative that you are looking for. So once again, if I take the derivative with respect to t of this expression, dv by dt is the derivative of 4/3 pi r cubed with respect to r times, r was a function of t, times dr by dt. Okay, so dv by dt is 4/3 pi times 3r squared times dr by dt, the inner derivative. Now, using the information given, you are given that dv by dt was equal to 1. Then on the right-hand side, you got 4/3 pi times 3 times, what was the radius at the point of interest? That was when r was equal to 10 times dr by dt. Now you solve for dr by dt, and you will get 1 over 400 pi centimeters per second. Okay, so take the derivative of the expression, use the chain rule where applicable, and then solve for the derivative that you are interested in. Okay, so you've got a right circular cylinder. Its volume is given by pi r squared h. Its diameter is increasing by 0.25 centimeters per second. That means its radius is changing by half of that. And its height is increasing by 30 centimeters per second. So you've been given dr by dt, and you've been given dh by dt. Okay, so v is a function of r and h, and both of those are functions of t, so we can regard the volume as a function v of t. And that's equal to pi times r is a function of t, which is then squared, times h of t. Now, if I want to find if I take the derivative on both sides with respect to t, I get dv by dt is equal to pi times the derivative of r of t squared times h of t. Well, now you can use the product rule. So that's r squared times dh by dt plus the derivative of r of t squared. So the derivative of r squared with respect to r is twice r. Then you have to multiply by the inner derivative, which is dr by dt, times h. Now, put in the given information. You were given that dh by dt was 30, and you were given that r was 45, so 45 squared here, and twice 45 here. And then half of 0.25, 0.125 times, you were given h. So plug all those numbers in. You get dv by dt is 77,625 pi centimeters cubed per second. Okay. Next example. So you've got an ellipse. The ellipse is given by the equation x squared plus 2y squared is equal to 6. There's a particle which moves on the ellipse over time, and you're given that so x is its x position and its y position are functions of time, and I'm going to assume at some point dx by dt is equal to minus dy by dt, and let's assume that the particle speed is never equal to 0. Okay, so differentiate the expression x squared plus 2y squared is equal to 6. Remember that x is a function of t and y is a function of t. So if you differentiate with respect to t on both sides, x is squared and x is a function of t. So the derivative of x squared with respect to x is twice x times the inner derivative is dx by dt plus the derivative of twice y squared with respect to y is 4y. And now you have to multiply according to the chain rule. You have to multiply by the inner derivative. The inner function was y, so times dy by dt. And the derivative of the constant 6 is equal to 0. Let's divide by 2, so I get x of t times dx by dt plus 2yt times dy by dt is equal to 0. Now, we are interested about the situation when dx by dt is minus dy by dt. So we have x of t times dx by dt plus twice y of t times dy by dt is equal to 0. Now when dx by dt is equal to minus dy by dt, this gives me x of t times minus dy by dt. Substitute in minus dy by dt for dx by dt plus twice y times dy by dt is equal to 0. Okay, so now I've got dy by dt, I've got something times dy by dt plus something times dy by dt. So put that together and factor out the dy by dt. So you got 2y of t minus x of t times dy by dt is equal to 0. If we're assuming that the particle speed was never equal to 0, that means that dy by dt is not equal to 0, because then both dy by dt and dx by dt at this point would be equal to 0, and the speed of the particle would be equal to 0. So dy by dt is not equal to 0. So something times dy by dt is equal to 0, and we know that dy by dt is not equal to 0. So thus we must conclude that 2y minus x is equal to 0 at that point. That implies that 2y is equal to x, and then y is equal to x over 2. Now go back to the original equation. If y equals x over 2, we substitute that into x squared plus 2y squared is equal to 6. X squared plus twice y was equal to x over 2 squared is equal to 6. I get 3/2 x squared is equal to 6, which gives x squared is equal to 4. So then this is happening when x is equal to plus or minus 2, which implies that y equals plus or minus 1. Okay, so that's giving the points where that the condition dx by dt equals minus dy by dt would hold.